Welcome back. In topic 4, we discussed in details about the characteristics and their mathematical implications for both plane Couette flow and pipe channel flow. In topic 5, we will apply those mathematical implications to simplify the mass, momentum, and energy conservation equations to obtain temperature profile and then find heat transfer coefficient and other convection variables. A. We will use example 5, plane Couette flow, to show how to simplify the governing equations to obtain the temperature profile and then heat transfer coefficient. 1. This is Couette flow, which is the flow of a viscous fluid in the space between the two plate surfaces. One is fixed, other is moving with velocity u. The two plates are separated by a distance h, and both have the constant surface temperature Ts. 2. The basic assumptions. A. The fluid is incompressible so that density is constant, and the fluid is Newtonian so that it follows Newton's viscosity law. B. The flow is steady so that all the derivative with time is 0, and the flow is two-dimensional in x and y direction so that the velocity and all the derivatives in the z direction is 0. C. The flow is laminar and hydrodynamically fully developed so that there's no acceleration and the velocity in the y direction is 0. D. The flow is purely shear driven so that pressure has no change in the flow direction and the gravity in the x and the z direction is 0. 3. The boundary conditions. First, for the velocity boundary condition, at y equals 0, the plate has 0 velocity. At y equals h, the plate has a constant velocity u. Second, for the thermal boundary condition, both plates have the same surface temperature Ts. Our goal is to find heat transfer coefficient H. 4. Now we will simplify the governing equations: continuity, 3 momentum equation, and 1 energy equation. A. Flow is steady, so all the derivative terms with time are gone. And the flow is two-dimensional in x and y direction. Therefore, all the derivatives in the z direction are gone. And the velocity in the z direction is 0. As a result, the momentum equation in the z direction is gone. B. The flow is hydrodynamically fully developed so that there's no acceleration, no velocity in the y direction. So continuity equation is satisfied. there's no acceleration. Velocity in the y direction is 0. The velocity in the y direction is 0. As a result, the y direction momentum is reduced to a static pressure equation. Velocity in the y direction is 0. C. Shear-driven flow. As a result, there is no pressure change in the x direction. There's no gravity. Finally, the x direction momentum equation become one-term equation, and energy equation become five-term equation. 5. After simplifying the momentum equations, we have one single term x direction momentum equation. Simply, we can integrate once, twice to get velocity profile. 6. Then we apply no-slip boundary conditions to get constant C1 and C2. Eventually, we get the velocity profile presented in equation 5.1. By checking, it is noticed the velocity change nearly along the flow direction. Since this is purely friction-driven flow, we can do an experiment. In this cavity, we have water. We let the air on the top to be blown away. You can see the friction carry the water flow. Since it's confined by the cavity, it forms a vortex. Interesting, isn't it? 7. Since we obtained the velocity profile, now we need to obtain a temperature profile. Equation 6 has 5 terms after satisfying the assumption of steady two-dimensional hydrodynamically fully developed. 8. We will apply new assumptions to further simplify the energy equation. A. There is no internal energy generation. B. It is a thermally fully developed Couette flow. So the first derivative and the second derivative of flow temperature is 0, 0. C. For shear-driven flow, of course, the viscous dissipation would not be 0. This is just like the tire of a car running on the road. It generates a lot of heat. Now let's check the viscous dissipation term. We will apply the two-dimensional in the xy direction. It is hydrodynamically fully developed condition to simplify, since there is no acceleration. So partial x is 0, and the velocity in the y direction is 0, so its derivative is 0 as well. So only one term left. Since we know the velocity distribution, we can get this derivative and plug in for the expression of viscous dissipation. 9. By checking the energy equation 6, after the simplification, we have one term and a second term left, which is represented by the constant. Next, we simply integrate once, twice for this second order ordinary differential equation. Then apply the boundary condition to get C1 and C2 to obtain the temperature profile. By checking, it is noticed this temperature for the plane Couette flow is only a function of y. It doesn't change along the flow direction. 11. Now we are knowing the temperature profile. Our goal is to find heat transfer coefficient. We need to obtain the derivative term and temperature difference term. First, we take a derivative of over y on the temperature profile, and then force y equals 0 to get its expression. Second, based upon the mean flow temperature definition, we integrate temperature profile and the velocity profile over the cross-section area, then divided by the mass flow rate to get its expression. Next, we combine the surface temperature Ts with the mean flow temperature Tm to get the expression for the temperature difference. 13. Now we can plug in the derivative expression here, the temperature difference direction here to get heat transfer coefficient, which is a constant if conductivity and the distance h are constant, which they are. 14. We finally can obtain the expression for Newton number, which is defined h times hydraulic diameter, because it is non-circular conduct, and divided by thermal conductivity. The hydraulic diameter is defined as full time cross-section area h time w divided by wetted parameter, which is 2w, because the side surface are not wetted. Then substitute the dh and h, we get a constant Newton number. F. For the pipe flow under the conditions of two-dimensional in x and r direction, steady, incompressible, and the energy and the conservation equations represented in the cylindrical coordinate. We have mass conservation, momentum conservation in the r and x direction. We have energy conservation and viscous dissipation, as well as the definition for the heat transfer coefficient and Newton number. 5, we have a basic assumptions. Flow is laminar and hydrodynamically fully developed. Flow is pressure driven, no internal energy generation, low speed flow to ignore the viscous dissipation, and thermally fully developed flow with temperature gradient constant, or the second derivative close to 0. With these governing equations and assumptions, we can simplify the 4 governing equations. The details will be presented in the PowerPoint slides. We only show the major steps. After simplifying the momentum equation and solve the only left x momentum equation, we obtained the velocity distribution inside the pipe, which is parabolic. After simplify the energy equation, we have 2 terms left with the velocity none under the thermal boundary conditions, symmetric at the center r equals 0, and the surface has a temperature Ts. We can integrate and obtain the temperature profile for constant heat flux thermal boundary condition, as well as for temperature profile for the constant surface temperature thermal boundary condition. By checking these 2 equations, it noticed this is only the function of r, and this is function of x. As a result, the temperature profile is function over both x and r. For this temperature profile, it's hard to obtain. As you can see, this is a summation of the series with constant defined right here. Finally, we have the temperature profile and the velocity profile. We can take derivative to get the first term and use the mean flow temperature definition to get temperature difference term to get the heat transfer coefficient. Finally, we plug H into the definition for the Newton number to get both Newton number for the constant heat flux thermal boundary condition and constant surface temperature thermal boundary condition. Both Newton number are constant. At this point, we covered topic 5. You expect to be able to simplify all the governing equations to obtain both velocity and temperature profiles, and then obtain the heat transfer coefficient and the Newton number. For case 1, the plain Couette flow with constant surface temperature thermal boundary conditions, and case 2 for the pipe and channel flow with constant heat flux thermal boundary conditions. See you next time.